On the first morning of the new year, January 1st, 3 Atlas crossed a region of space just visible from the cloud tops of Jupiter. For months, telescopes had tracked its oddities, the jets, the solar-aligned emissions, the structural defiance. But now something changed. The object was no longer being studied only from Earth. It had reached a position where, from the gas giant's orbit, observers could triangulate a different perspective, not from below, but from beside. What they saw from that vantage shouldn't have been possible. From Jupiter, 3 Atlas didn't behave like any known interstellar body. It shimmered with patterns, moved with precision, and interacted with light in ways that suggested intention, not randomness. It became clear that observing this object from Earth alone was never enough. You had to move out. You had to stand beside it on the shoulder of giants to truly understand what it was doing. This is not a story about distance. It's a story about alignment, because from Jupiter, everything looked different, and that difference might change how we understand 3I Atlas forever. From the gas-shrouded edge of Jupiter's orbit, a new perspective emerged. Not of the planet itself, but of something smaller, stranger. For weeks, Earth-based astronomers had tracked 3I Atlas with growing concern. Its jets defied thermal logic. Its tail was spiraling instead of streaming. Its sudden brightness flares made less and less sense the closer it came to the Sun. But on the morning of January 1st, the object finally aligned in such a way that it could be observed not from below but almost beside, from the outer solar system's second vantage point. And what came into view from Jupiter shouldn't have been possible. At first glance, it still resembled a comet, a faint core, a coma of gas, and a long tail glowing faintly in reflected sunlight. But the shape was wrong. The tail didn't taper off into randomness. It curled, coiled. From Jupiter's lateral view, the tail curved not as a blur of gas, but as a formation, something tight, almost braided, like filaments winding around an invisible spine. That wasn't just a trick of angle, it was structure, and structure implies order. This perspective had never been available before. From Earth, 3I Atlas's trajectory created a foreshortened effect. Everything stacked, tail, coma, core, like looking straight down a hallway of light. But Jupiter, sitting roughly 45 degrees off that vector, revealed a profile. And that profile changed everything. Multiple observatories stationed across Jupiter's moons, including Callisto and Ganymede, began collecting synchronized data. The Juno spacecraft, though designed for Jupiter's magnetosphere, was still equipped with wide-angle spectrometry. Together, they formed a temporary triangulation network, an accidental array, and when their data was combined, it revealed something both elegant and disturbing. The jets weren't venting randomly, they were aligned. Each emission from the object's surface traced a narrow arc, perfectly symmetric along its equatorial axis. Instead of spreading chaotically, they held their formation like beams. Most jets from comets widen the farther they travel. The particles disperse. But here, the beams held together for thousands of kilometers, coherent, unwavering, and geometrically balanced. More curious still, the jets didn't align with the solar vector. From Jupiter's view, the Sun was off to the left. The jets were firing at an angle, not away from the heat source, but rotated roughly 30 degrees off axis. When traced, their intersection point wasn't the Sun, but a region of space closer to Saturn's orbit. That orientation didn't match any known thermal or gravitational behavior. It matched a pattern, a decision. And then came the polarization data. Light bouncing off 3I Atlas was filtered through Jupiter's magnetic envelope, one of the strongest in the solar system. This allowed observers to see with greater clarity how the object interacted with radiation. The result was a clear signature, partial polarization, not from dust scattering, but from a smooth, coherent surface. As if light was reflecting off panels, not clouds. From Earth, these reflections had been interpreted as flares, temporary brightness surges, likely caused by jets or volatile outbursts. But from Jupiter, they took on a different character. They were timed, rhythmic, and they repeated. In essence, Jupiter had given us the one thing we didn't have, depth, and in that depth, the mystery doubled. What we had called a comet was now acting like a machine. What we thought was randomness became signal, and what we assumed was chaos turned out to be control. The outer world had shown us something Earth could not. Not a new object, but a new dimension of it. And this was just the beginning. If Earth is a noisy room, Jupiter is silence, not because of distance alone, but because of insulation. The gas giant's magnetic field, the largest and most intense in the solar system, forms a kind of shield, a cocoon that buffers the inner noise of solar interference. Radio storms that saturate Earth's near-space environment get diffused here. Charged particles that would scramble sensors are trapped in the belt surrounding Jupiter instead. And for the first time since the discovery of 3I Atlas, we had a clean signal, unfiltered, undistorted, and uninterrupted. From this magnetic stillness, the object revealed its second face. The instrument stationed on Europa, particularly the long baseline spectropolarimeter, recently repositioned to track inbound asteroids, captured a continuous observation window of nearly 11 hours as 3I Atlas rotated past its optimal angle. What they recorded wasn't just reflected light, it was modulated light. Light that changed not in colour, but in alignment, shifting degrees of polarization across a predictable pattern. It was as though the object had facets, angular planes that swept light differently depending on its position relative to the observer. On Earth, these kinds of measurements are often dismissed as atmospheric artifacts or diffraction errors, but Jupiter's lack of dense upper atmosphere makes those excuses fall away. And when cross-validated with Juno's trailing observations behind the gas giant's limb, the data aligned. The object was reflecting light in a way that suggested not randomness, but geometry. This isn't how comets behave. Natural objects scatter sunlight diffusely, like fog in headlights. The dust in a comet's coma tends to polarize light minimally and inconsistently. But what Jupiter saw was something else entirely. A rhythmic polarization curve, one that repeated itself across every full rotation of the object. That means the reflectivity of 3I Atlas wasn't isotropic. It was directional, predictable, almost mechanical. Even more telling was the shadow phase. During one crucial 47-minute period, the object passed through the outer umbra cast by Jupiter's limb. From this angle, sunlight was partially blocked, enough to reduce incoming radiation but not fully plunge the region into darkness. What occurred next startled every observatory watching. Instead of dimming uniformly, 3 Atlas exhibited what observers described as angle-preserving persistence. In simpler terms, it held its brightness, not fully but with a reduction far smaller than predicted by the drop in illumination. Something was compensating, not emitting light, but maintaining reflectivity despite less input. One model suggested an internal delay, like a material with a thermal memory or a capacitive optical response. But those are properties found in engineered surfaces, not dirty snowballs drifting from another star. If the object was passive, it should have faded. Instead, it shimmered. Not as a constant beam, but as a pulse. And that pulse carried across multiple wavelengths, from near ultraviolet to the lower edge of infrared. That range is important. It implies multi-surface reflectivity, or coatings that respond differently across the spectrum. What caused this behavior remains an open question. Was it simple coincidence, a property of unusual ice under unique conditions, or was this a feedback system, a surface designed to maintain optical presence even under variable light? From the Jovian lens, what became clear wasn't just how strange the object was, but how consistent it had become. The inconsistencies that had baffled Earth-based observation were now resolving into patterns, not randomness, but rhythm, not chaos, but choreography. Earth had been hearing noise. Jupiter had found the signal beneath it, and in the silence of the outer worlds, 3I Atlas had begun to speak more clearly. For weeks, one anomaly had captured the attention of every observatory tuned to 3I Atlas, the anti-tail. A feature that shouldn't exist, at least not in the way it appeared. It pointed sunward, opposite of everything standard comet physics predicted. At first, it was dismissed as a viewing angle trick, a parallax effect caused by Earth's orbital position. The dust trail left behind, they said, had simply lined up with our perspective. But as the comet moved, Earth moved too. The angles changed, the anti-tail didn't. From Jupiter's vantage point, that contradiction sharpened. The anti-tail, long believed to be an Earth-centric illusion, now stood exposed in 3 dimensions. Observations from both Juno's forward visual payload and a recently recalibrated imaging spectrometer on Ganymede revealed something striking. The anti-tail wasn't an illusion. It was real, it was spatial, and it wasn't aligned with the Sun at all. Instead, the tail was pointing along a plane that intersected not with the solar vector, but with Saturn's orbital corridor. In other words, from Jupiter's angle, the anti-tail wasn't a backward trail or a static emission. It was directed, oriented. It wasn't a ghost of material left behind. It was active. And it was aiming. This discovery unsettled more than just the scientists who had spent weeks modelling solar wind vectors and dust particle trajectories. It forced a re-evaluation of what a tail even meant in this context. Because if a stream of material from a supposed comet is not being dictated by solar pressure, but by planetary geometry, then it might not be a tail at all. It might be something else entirely, an output, a signature, a signal. The anti-tail extended for nearly 100,000 kilometres, yet it maintained coherence across that span. From Earth, it shimmered with a diffuse glow, occasionally flickering as if distorted by interplanetary dust. But from Jupiter, where that dust was largely absent, the line resolved into something narrower, more refined. Its thickness varied over time, expanding slightly every 5 hours, then contracting again. That rhythm matched no solar cycle, but it did match Saturn's radio emissions, specifically the periodic signal drift from Saturn's kilometric radiation, a known electromagnetic cycle that pulses through the outer solar system. Why would an interstellar object hundreds of millions of kilometers away be synchronizing with Saturn's radiation belt? Theories began to surface. Some proposed that the tail was simply reacting, that the particles being ejected were charged and lining themselves along ambient electromagnetic fields. But no other comet had ever demonstrated this kind of synchronized directional behavior before, not even ones passing much closer to Saturn. Others speculated that 3I Atlas wasn't reacting at all. It was navigating. This idea was difficult to digest, even for the more open-minded research teams. But the geometry was hard to ignore. The anti-tail wasn't just aligned with Saturn, it pulsed in that direction, and not in a chaotic, fluctuating way, but in phased bursts, as though emitting something regularly. From Jupiter, this directional behavior became unmissable. In past comet studies, anti-tails were transient, dissolving as quickly as they formed, always tethered to the observer's position. Here, the anti-tail defied that expectation. It remained fixed, even as both Earth and Jupiter moved significantly in their respective orbits. From 2 planets and 5 instruments the direction held. And that changed the question entirely. The mystery was no longer, why is there an anti-tail? It became, why is the anti-tail pointing there? If this object had intention, if its emissions were being shaped not by passive forces, but by spatial alignment, then what we were witnessing wasn't just a rare comet. We were watching behavior. From Jupiter, the anti-tail no longer looked backward. It looked forward. The discovery didn't begin with a burst. It began with silence. On the far side of Jupiter, deep within the protective shadow of its immense magnetic field, a region known for its electromagnetic tranquility, the Europa-bound probe Vireo was conducting routine sky monitoring. Its mission wasn't focused on 3I Atlas. In fact, the object was supposed to be too faint, too distant, and partially occluded behind Jupiter's own radiation belts. But on the morning of January 1st, during a scheduled calibration sweep, Vireo's ultraviolet sensors captured something it wasn't looking for. A pulse, sharp, isolated, and then, 48 minutes later, another one. It didn't come from Jupiter. It didn't come from Europa. It came from a fixed point in space, a point later triangulated to the outer limb of 3I Atlas, rotating slowly as it arced away from the Sun. At first it was assumed to be background noise, cosmic ray interference or a remnant echo from a solar event. But over the next 6 hours the pattern repeated. 6 identical pulses, each spaced 48 minutes apart, each one originating from the same position relative to the object's body. Not random, not chaotic, but rhythmic. And crucially, these pulses were coming from the night side. This detail changed everything. Cometary emissions are typically driven by solar input. Volatiles sublimate when warmed by sunlight, triggering jets and flares, all of which occur on the illuminated hemisphere. But this signal was different. It came from the dark, from the side of 3i Atlas that was in total shadow, receiving no direct solar radiation at all. Further analysis revealed that the signal wasn't in the visible spectrum. It hovered in the near-ultraviolet range, just beyond what the human eye can perceive, a band often used in spacecraft communications and atmospheric studies because of its clarity in vacuum conditions. The pulses lasted between 1.2 and 1.4 seconds, short enough to feel transient, but long enough to rule out accidental interference. The next confirmation came from the Jovian moon Ganymede, where a sensitive array of optical sensors managed to detect weak echoes of the same pulses, reflected not in ultraviolet but in low-band infrared. This suggested something even more curious, that the pulses weren't being emitted equally in all directions, they were shaped, directed. Narrow beams that swept laterally, not outward. In practical terms, they were visible only if you stood in their path, like a lighthouse beam slicing through the dark. And Jupiter, as it turned out, was standing in just the right place. What could cause a cold, dark object millions of kilometers from the Sun to emit directional pulses at regular intervals? Some scientists pointed to thermal instability. Perhaps heat stored during perihelion was being released unevenly, but that wouldn't explain the consistency, nor would it explain why the pulses were confined to a narrow wavelength band. Others suggested a chemical or quantum effect, that exotic ices from its interstellar origin were undergoing phase transitions when passing through Jupiter's magnetosphere. But again, that would produce noise, not rhythm, not 48-minute intervals, not beams. The most controversial theory came from a group at the European Southern Observatory, that the pulses were part of a spin-linked signal, that a surface feature, perhaps a reflective plate or crystalline formation, was rotating into position every 48 minutes, momentarily aligning with Jupiter and reflecting a source of ultraviolet light. But the only nearby light source was the Sun, which was blocked by the object's own mass. There was no direct line of sight, which meant one thing: the light was coming from within. From the dark side of 3i Atlas, something was emitting, regularly, cleanly, quietly, and Jupiter was the only place in the solar system positioned to notice. Just after midnight on January 1st, a superstorm unfolded over Jupiter's northern hemisphere. Designated JN 121A by planetary scientists, the cyclone wasn't extraordinary by Jovian standards, but it was notable for its brightness. The storm's upper cloud layers reached unusually high albedo values, briefly transforming a patch of Jupiter into a blazing white beacon visible even through Earth-based telescopes. At the same time, nearly 1.7 astronomical units away, the Juno spacecraft captured something unexpected. Positioned just beyond Jupiter's equatorial limb, Juno was not looking at the storm directly. It was focused on open space, toward a region where 3i Atlas was passing. What it saw defied simple reflection models: a flash, brief, sharp, and mirrored back toward the direction of the storm. Not solar reflection, that angle was wrong. Not radiation interference. The electromagnetic logs were quiet. What Juno recorded was a visual phenomenon, a momentary beam of light returning from the object's surface, aligned not with the Sun, but with Jupiter itself. When investigators traced the angle of incidence and reflection, the geometry converged perfectly. The light from Jupiter's storm had travelled outward, struck the surface of 3i Atlas and bounced back. That kind of reflection, precise, directional, mirror-like, requires something specific: a smooth surface, not ice dust, not gas particles, a solid, reflective plane. This wasn't the first time something like this had happened. Months earlier, Earth-based telescopes had documented a series of sudden brightness surges, flashes dismissed as jet activity or volatile outbursts. But those surges lacked follow-up data. They had been written off as coincidence. This time, the data was clearer. The reflected light wasn't diffused. It returned in a coherent column, detectable by both Juno and, several seconds later, a photometric relay sensor aboard the Ganymede orbital station. The delay between those detections gave analysts a rare opportunity: triangulation. And what they discovered sent chills through the research community. The reflection hadn't come from a curved or uneven surface. It came from a defined patch, an area no larger than 20 square meters. In that brief moment, Juno's camera recorded something no one expected, an angular shape, not organic, not fragmented, but geometric. For less than a second, as the reflected light illuminated the body of 3I Atlas, a hexagonal pattern appeared across its midsection. It wasn't luminous, it wasn't glowing, it was revealed, etched, embedded, repeating. The structure didn't last long. As the object rotated, the light angle shifted and the feature vanished, drowned again in the grey blur of its outer shell. But the data had been captured. The hexagonal imprint appeared in 3 separate frames, each taken 0.3 seconds apart, enough to confirm its symmetry and scale. What natural process could create a hexagonal structure on an interstellar object? On Earth, hexagons appear in cooled lava, dried mud, and crystallized salt, systems where equilibrium and surface tension favor efficiency. In planetary systems, Saturn's North Pole hosts a famous hexagonal jet stream created by atmospheric dynamics. But on a small interstellar body, with no atmosphere, no tectonics, and no observable chemistry on that scale, there is no precedent. None. It didn't look accidental. It didn't look broken. It looked designed. Still, the scientific community hesitated. No one wanted to jump to conclusions. Yet as the data spread, a quiet consensus began to form. The flash wasn't a flare, it was a mirror. And what that mirror briefly revealed was not a crack, but a symbol. A formation that couldn't be explained away by dust, heat, or distance. From the surface of Jupiter, that flash was invisible. But from Juno's angle, silent, shielded, and cold, the reflection whispered something strange. There's a shape inside the mystery, and it's not random. On January 1st, 2026, the magnetic field around Jupiter, one of the most powerful and expansive structures in the solar system, recorded something subtle but strange. Juno's magnetometer, a device that had long since settled into a rhythm of predictable readings, logged a localized distortion. It wasn't violent, it wasn't chaotic, it was simply wrong. A smooth deflection in the background field, extending for nearly 25 minutes, that returned to baseline without a known cause. And crucially, it didn't match any solar wind event, internal Jovian storm, or Io-driven plasma plume. It came from outside. The trajectory of the anomaly pointed to open space, beyond the orbit of Callisto, specifically to the narrow corridor where 3I Atlas had just passed. At first this seemed implausible. Comets don't interact with magnetic fields at this scale. They carry no charge, they generate no field. Their contribution to surrounding magnetism is negligible. Even when sublimating near the Sun, their effect is strictly chemical, trails of ions and dust blown out by radiation pressure. But this object wasn't near the Sun. It was drifting through the outer solar system, cold and silent. Yet the data said it was still doing something. Further analysis by the Jovian Magnetosphere Initiative, a multi-agency collaboration based on Earth, revealed that the shape of the disturbance was consistent with a moving field envelope. In other words, it resembled what happens when a magnet passes slowly near a sensitive coil, a gentle induction curve, rising, peaking, falling, clean, linear, not explosive like a solar flare, not chaotic like Io's plasma wake. The implication: the object had interacted with Jupiter's magnetic field, not by being affected, but by modifying it. That kind of effect requires one of two things, either a significant internal field of its own, or a surface composition capable of distorting external fields through passive or active means. Neither should apply to a comet, but this wasn't behaving like a comet. Simultaneously, sensors aboard the Europa orbital station registered a brief increase in induced current along the edge of the magnetotail, the long-stretched region of Jupiter's magnetic field blown outward by the solar wind. These currents were measured at frequencies typically associated with artificial resonance, not the slow, rolling shifts caused by natural field drift. When researchers overlaid the current spike with the path of 3I Atlas, something remarkable emerged, a perfect temporal overlap. The current peaked precisely as the object crossed the tail's magnetic boundary, then it faded, cleanly, as if something had passed through, interacted and moved on. Still there was no emission, No light, no jet, no outward sign. The body remained visually inert. It tumbled slowly, its tail drifting behind it, the hexagonal pattern long gone from view. But the field remembered. Some theorized that the object might be wrapped in a thin conductive sheath, a shell of carbon-rich material or ultra-dense nickel, both of which could distort field lines without generating their own charge. Others went further. They suggested the object was not simply passing through Jupiter's field, but using it, riding it like a rail, skimming the edges of magnetic boundaries to conserve energy or navigate space more precisely. That idea remains unproven. But the models support one thing. This wasn't random. The shape of the field distortion, the timing of the induced current, the absence of any solar driver, all of it points toward intentional interaction. And if a passive body interacts with a planetary field in a repeatable, structured way, it may not be passive at all. The silence of space is often mistaken for peace, but in this case, silence concealed precision. And Jupiter, the solar system's magnetic giant, had just been brushed by something that acted like it understood the rules, and then rewrote them. By all conventional models, 3I Atlas should have still been warm. After its perihelion months earlier, the object had absorbed intense solar radiation. As it departed the inner solar system, that heat should have slowly dissipated, bleeding into the vacuum of space like steam from a cooling ember. Most cometary bodies take weeks, even months, to return to their thermal baseline, especially if they've been active, venting gas and dust, exposing fresh ice, and altering their surface layers. But on the morning of January 1st, data from the Ganymede infrared monitor told a different story. From over 700 million kilometers away, its calibrated spectrometer captured thermal emission lines from 3I Atlas. The results came back lower than expected, far lower. The surface wasn't just cooling faster than predicted, it had dropped below the expected baseline altogether. The object's thermal signature had plateaued at an effective temperature nearly 40% lower than post-perihelion models allowed. This wasn't a comet losing heat, it was something controlling it. That kind of drop cannot be explained by shadowing or rotational effects alone. Even if the object had spun a cold face toward the sun, the residual heat from its inner layers would have continued radiating outward. But here, the entire body cooled simultaneously, uniformly, as if whatever mechanism had driven its internal warmth was now actively reducing it. To test the readings, a second thermal sweep was performed 90 minutes later from the Europa surface station, using an alternate lens. The numbers confirmed the same curve. It wasn't a spike or a sensor anomaly, it was a pattern. What could cool a celestial object so rapidly and so evenly? Some scientists pointed to surface chemistry. Perhaps the exterior of 3I Atlas contained exotic ices with ultra-high emissivity, capable of radiating heat more efficiently than anything in our solar system. Others invoked a porous interior, a foam-like structure that allowed heat to conduct inward and distribute quickly, dropping the overall surface temperature. But there was a problem. The reflectivity hadn't changed. The object was still bouncing back light in the same UV and IR bands as before. If it had simply cooled due to deep space exposure, its optical characteristics should have dimmed, especially in the higher wavelengths. They didn't. Instead, the emissions sharpened. That led to a far more controversial hypothesis: thermal regulation. On Earth, spacecraft use radiator panels, phase-changing materials, and gold foils to manage internal heat. Not to keep warm, but to avoid overheating. Out in deep space, temperature management is everything. But no natural object has ever displayed signs of thermal self-regulation, until now. If 3I Atlas was somehow redirecting its heat, storing it, absorbing it, or shedding it, then it wasn't just reacting to its environment, it was managing itself, not through fire or eruption but through stillness. Quiet, deliberate, unexplainable stillness. From Jupiter's orbit, that stillness became almost poetic, an object adrift, silent and dark, cooling itself as if preparing for something. Not decay, not fragmentation, but transition. The silence of cold is not always the end of a journey. Sometimes it's the beginning of control. Most gravitational measurements in our solar system focus on large bodies, planets, moons, and occasionally asteroids large enough to nudge nearby spacecraft. Smaller objects, especially interstellar passers-by, don't leave detectable ripples in the gravity field. They're too light, too distant, too fast. But 3i Atlas had once again defied expectation. On January 1st, during a routine orbital refinement update, the Ganymede tracking array logged a minuscule but measurable anomaly in its local acceleration readings. The numbers didn't make sense. For nearly 12 seconds, one of the array's outer satellites recorded a shift, a nanometric compression in its orbital path, as though something had passed nearby with gravitational mass. This shouldn't have been possible. 3i Atlas was hundreds of thousands of kilometers away. Its mass was estimated to be in the range of a mid-sized comet, enough to affect local dust maybe, but not influence an orbital system stabilized by Jupiter's immense gravity. And yet, when the data was cross-referenced with Europa's subcrustal seismic station, a device designed to detect gravitational tidal shifts beneath the Moon's icy shell, another echo appeared. The same timestamp, the same slight impulse, the same direction, two independent systems, one gravitational whisper. Astrophysicists rushed to model the anomaly. The only solution that made sense on paper was that 3i Atlas wasn't acting as a point mass, but as a variable mass, something that for a few seconds appeared heavier than it should. That concept has no precedent in celestial mechanics. Mass doesn't just appear, it doesn't change moment to moment. But here, for a brief window, 3i Atlas had exerted a gravitational influence stronger than its known size and density could support. Not enough to destabilize anything, but enough to register, barely, on the most sensitive instruments orbiting Jupiter. Some suggested it was a dense core, perhaps a chunk of ultra-heavy material deep inside the body. Others posited that the object passed through a weak gravitational lens, a curvature in space caused by another invisible mass. But there was no such object nearby, no rogue planet, no dense asteroid, no explanation. Unless, of course, the mass wasn't constant. Unless the object could, somehow, shift its own gravitational profile even briefly. Not by becoming heavier, but by concentrating mass along one axis, or bending space in a localized field. Impossible by all known laws, and yet, here we are. On January 1st, in the stillness of the Jovian system, something echoed. Not acoustically, not electrically, but gravitationally. And that echo had a shape, a curve that shouldn't exist. The space between Earth and Jupiter is often thought of as empty, a void filled only with solar wind, drifting dust, and the occasional charged particle from cosmic rays. But it's also a communication channel. Across that gap, spacecraft relay data, probes transmit telemetry, and observatories share silent signals to and from the inner and outer planets. For most of human observation, that corridor is unbroken, a quiet highway for information moving at light speed. But in the hours surrounding January 1st, something changed. At exactly 3:32 UTC, a series of relay packets sent from the James Webb Space Telescope en route to a deep sky data hub on the far side of the Moon were delayed. Not dropped, not corrupted, just late. By 1:42 seconds. Then, 12 minutes later, the same delay occurred on a packet routed through the Mars Reconnaissance Network. Then again, this time from the ESA's Deep Space Antenna in New Norcia, Australia, bouncing a telemetry confirmation to Juno via Earth-Jupiter protocol. Each time the signal passed through the same corridor, a long straight slice of interplanetary space now occupied by a single drifting object, 3i Atlas. What's important here isn't the delay itself. Space weather can affect timing, solar wind can interfere with velocity, but what raised alarm was the precision. The signal delay appeared at exactly the same spatial alignment, each time the transmission crossed a narrow window of degrees that intersected 3i Atlas's current location. Not near it, not broadly within its trajectory, right through it. That alone would warrant attention. But there was more. Following the third delay, the New Norcia team manually altered the signal angle by just 0.2 degrees, a standard calibration test. The signal passed cleanly, no delay. The moment the beam no longer intersected with 3i Atlas, the lag vanished. This suggested one of two things. Either the object was acting as a medium, slightly distorting or refracting the signal, or it was interacting with it directly, To test the idea, a low-frequency test ping was sent from ESA's Mars relay back toward Earth, timed to intersect 3I Atlas's field vector. The return signal arrived intact, but something was off. A barely measurable low-band oscillation was embedded in the waveform, a modulation not present in the original transmission. Not noise, not interference, a structure. Think of it like this. Imagine sending a radio tone through a tunnel and hearing it return with a rhythm, like someone tapping a spoon along the wall as it passed through. That's what happened here. The modulation did not resemble known patterns from reflection, interference, or signal degradation. It resembled a signature, as though something had read the packet and responded. No claim was made, no public admission. But within hours, both NASA and ESA reclassified the corridor as temporally sensitive. All automated routing protocols were adjusted, signal paths were altered. 3I Atlas was no longer just an object being tracked. It had become a node, a point in space that needed to be accounted for during transmissions. To the public, the changes were invisible, but to the people watching closely, a question emerged. If 3I Atlas could delay, redirect, or imprint upon a signal, then it wasn't just reflecting light anymore. It was listening. After the unexpected signal modulations from the Earth-Jupiter corridor, analysts at the Jet Propulsion Laboratory began a deeper sweep, looking for secondary harmonics, waveform drift, or low-frequency echoes embedded in the delayed transmissions. What they found wasn't noise, it was consistency. On 3 separate occasions, the return ping, the signal bouncing back from Juno, Mars, and the Webb telescope, carried with it a faint repeated signature. Not enough to trigger a communication flag, not strong enough to decode, but regular enough that it couldn't be dismissed. The signal pulsed at 0.0228 Hz, just one beat every 35.7 seconds, barely measurable, almost beneath the noise floor. But there it was, matching in amplitude, shape, and phase across multiple signal paths. A slow, gentle ripple, like a drumbeat under deep water. More tests were conducted, different frequencies, different angles. They changed the carrier signal, swapped out the encoding format. Each time the signal passed through the 3I Atlas corridor, the same 0.0228 Hz pulse returned, steady, quiet, unchanging. This wasn't an echo, it was a fingerprint. To test the hypothesis further, a bold experiment was approved. ESA's Deep Space Array in Malag, Argentina, transmitted a null signal, a carrier wave with no encoded data. No message, just an empty hum. This kind of signal is often used to test for signal degradation or radiation scatter. The signal reached the object's corridor. It returned 1 minute later. Embedded inside that blank return, the same pulse, same strength, same spacing. But this time, there was something new. For 3 of the 35.7 second intervals, the pulse skipped, just slightly. Not erased, just missing the peak of its waveform by a fraction of a millisecond. Then, it corrected. The signature realigned. This caused immediate debate. Some researchers argued it was a transient ionization event, particles in the corridor temporarily interfering with the return, but ion interference doesn't skip in perfect cadence, it doesn't self-correct, and it certainly doesn't drift, then snap back into sync as if adjusting to a metronome. The more daring theory began to circulate, quietly, in internal forums flagged as speculative, that the signal wasn't interference at all, it was a response, or at the very least, an acknowledgement. The corridor had been used for decades without issue. No object, natural or artificial, had ever left a consistent imprint on a signal like this. Yet now, as 3I Atlas drifted along its outbound path, it was becoming less of a comet and more of a gate, a lens, a reflective surface not of light, but of intent. If it was coincidence, it was mathematically elegant. If it was natural, it was too perfect. And if it was something else, we had just sent a signal through the void, and something in the dark tapped it, and tapped back. At first glance, the clouds of Jupiter seemed to behave as always, swirling with furious wind belts, showcasing the iconic red storm spinning across the southern hemisphere. But when researchers adjusted contrast levels on composite imagery captured from orbit, something else emerged. Beneath the great red spot in the shadowed undercurrents of the storm's base, a pattern began to form, one that wasn't generated by atmospheric dynamics alone. These were not shadows cast by moons or the optical tricks of light diffusion. The contours appeared geometrically stable, fixed in shape even as the surrounding storm rotated. Almost like a slow-moving fingerprint, dark lines traced across the boundary between gaseous mass and the depths below, matching, with eerie precision, the outline of 3I Atlas's most recent silhouette as seen from Earth just days earlier. Teams from both the European Space Agency and independent observatories began layering these frames over the comet's known dimensions. The alignment was too close to ignore. And while no one dared use the word replication, whispers of mimicry threaded through astrophysics forums. Was Jupiter absorbing the object's visual imprint, or was Atlas projecting something toward Jupiter's atmosphere? The shapes weren't random. Every few hours they shifted slightly, rotating in a direction opposite to the planet's spin. Their arrangement mirrored the strange internal formations once spotted in the comet's tail sheath, a set of triple-lobe structures first observed during its trajectory around the Sun. That same trifold geometry was now appearing as a negative space under Jupiter's storm belt. It wasn't just a reflection, it was a response. By midday, remote sensing stations flagged a rise in thermal anomalies directly beneath the red spot's base. This wasn't heat from above, it was emerging from below, slow, pulsing, almost breathing. The data was clear. Something inside Jupiter, long thought untouchable, was stirring. And its first visible signal came in the form of a shadow, shaped like 3I Atlas. Jupiter has always been a magnet for electrical storms. Its internal dynamo creates lightning strikes more powerful than anything on Earth. But shortly after the strange shadow forms appeared beneath the red spot, the planet's lightning began to change direction. Not literally, but functionally. Instead of erupting from the deeper atmospheric layers and branching upward, new bursts were recorded originating from the uppermost cloud bands and diving downward. It defied all known models. From above, the strikes were barely visible, but when captured through ultraviolet sensors, their structure revealed a strange symmetry. They spiraled inward, not outward, and most disturbing of all, they followed magnetic field lines that had previously been mapped as dormant. A lattice of dormant conduits suddenly lit up with synchronized pulses, threading across Jupiter's equator, then branching toward the poles like an invisible grid. High-resolution instruments aboard the Juno probe recorded a soft rise in magnetic intensity near the polar vortex. These weren't random fluctuations. They spiked with rhythmic consistency, every 6 hours, mirroring Atlas's own earlier pulses observed near Earth's magnetotail weeks before. What was once considered a one-time phenomenon, Atlas's directional frequency emissions, now seemed to echo inside Jupiter's magnetic scaffolding. The lightning was responding. And so were the clouds. Bands of gas that once flowed in predictable belts began twisting at their edges, almost as if responding to invisible guide rails. Deep learning models trained on atmospheric dynamics couldn't replicate the pattern. The shift wasn't from heat convection or gravitational pull, it was directional, intentional. Jupiter wasn't just absorbing energy, it was redirecting it. And somewhere in that transfer, 3I Atlas's presence, no longer near the planet but visible from its surface, appeared to be shaping the flow. From a moon's distance away you would see the upper clouds ripple, not from wind but from current. And in the rarest moments, you might catch a strike from the sky, falling back into Jupiter, as if returning home. Jupiter's many moons have always been a theatre of geological drama, Io with its sulfuric eruptions, Europa, hiding a possible subsurface ocean beneath a cracked icy crust, Ganymede and Callisto, each with their unique magnetic anomalies. But after the atmospheric shifts and magnetic pulses on Jupiter itself, something unusual began to unfold across its largest satellites. Not just seismic changes, but resonance. The first anomaly came from Ganymede. As the largest moon in the solar system, and the only one with its own magnetic field, it was uniquely positioned to act as a kind of amplifier. On December 29th, its internal magnetosphere began oscillating slightly, not in chaotic bursts, but in a rhythmic sequence, 3 pulses every 10 minutes. These pulses were captured by the European JUICE probe as low-frequency waves, like a distant heartbeat buried beneath layers of rock and ice. At first, this was dismissed as random electromagnetic turbulence caused by the solar wind, but when similar pulses were then detected on Europa and Io, each in perfect synchronization with Ganymede, astrophysicists were forced to reconsider. These moons are vastly different in composition and behavior. There's no reason for them to pulse in unison, unless they were reacting to the same source. Enter 3I Atlas. Spectrographic comparisons between the pulses now radiating across the Galilean moons and the signal burst that Atlas emitted while passing. Earth revealed a near-identical profile, narrow band, low frequency, and perfectly spaced. The object, though no longer visible from the Jovian system, had left a resonance behind, like a bell rung hard enough to keep echoing through stone. But there was more. Io's volcanic emissions, typically sporadic and chaotic, began releasing in patterns, regular intervals of discharge as if syncing with the magnetic pulses. Volcanologists at Caltech noticed that the thermal signatures weren't just increasing, they were concentrating toward Io's sub-Jovian hemisphere, the side always facing Jupiter. That was unprecedented. Europa, on the other hand, began to show oddities in its ice. Cracks that once formed naturally from tidal stress were now aligning toward specific coordinates, each pointing at different angles but converging toward a singular magnetic focal point on Jupiter's equator. And Ganymede, its auroras grew brighter, more structured. Instead of faint streaks of charged particles dancing over its poles, its magnetosphere began shaping them into loops, clean spiraling arcs that matched the formation of Atlas's tailsheath geometry. This was no longer geological behavior, it was mimicry. Jupiter's moons were responding not to gravitational changes, but to information, pulses, rhythms, frequencies, encoded in the electromagnetic storm that 3I Atlas had somehow triggered before vanishing from the planet's view. The moons weren't just reflecting the signal, they were relaying it. Across crust and core, through ice and volcanic flow, the entire Jovian system had become a sounding board. Something had awakened a network, and it didn't originate from Jupiter. While eyes remained fixed on Jupiter's atmosphere and its dancing auroras, teams at the European Southern Observatory began turning their attention below the surface. New infrared mapping tools, originally designed to detect geothermal flux on exoplanets, were retrofitted to scan the giant planet's deeper cloud layers and, more controversially, its potential interior heat anomalies. What they found was staggering. Across a band stretching 15 degrees north of Jupiter's equator, narrow plumes of subsurface heat began to rise. Not with volcanic chaos, but with uniformity. These were no random hotspots. They formed a chain, evenly spaced, like a buried array stretching halfway around the planet. Even stranger, they pulsed. Every 4 minutes, each heat well flared by approximately 1.3 degrees Kelvin, then cooled, then flared again. The cycle was consistent across every point, even those separated by thousands of kilometers. More disturbing still was their vertical origin. These heat flares weren't coming from the upper convection layers. They were sourced deeper, much deeper. Using adaptive optics to model refracted signals through the gaseous layers, scientists estimated that the source of the pulses originated close to Jupiter's metallic hydrogen zone, a region so pressurized it behaves like a liquid metal, generating the planet's colossal magnetic field. For decades, this zone had been inaccessible to direct measurement, but now it was flashing. A team from NASA's Deep Atmosphere Research Initiative ran the data through simulation engines. The pattern resembled the early phases of an engineered heat sink, a structure designed to distribute energy evenly across a hostile environment. On Earth, such structures exist only in fusion experiments and advanced reactor cores, but here it was, embedded inside a gas giant with no solid surface. That left only two possibilities. Either this pattern was the result of a natural mechanism we had never witnessed before, or something had seeded this zone with structure. Some astrophysicists cautiously proposed the idea of sympathetic activation, the notion that a passing object with unique electromagnetic properties could resonate with latent materials and bring them into alignment. And Atlas fit that description perfectly. The geometry matched, the pulse cycle matched. Even the timing matched. The heat wells began activating only after 3I Atlas passed the L2 gravitational corridor between Jupiter and the Sun, a region known for subtle tidal interactions but never for magnetic induction. Now, with these deep heat wells forming an almost architectural signature, Theories that once belonged to science fiction were resurfacing in serious papers. One theory in particular gained traction: that 3 Atlas wasn't leaving traces. It was triggering dormant systems, and Jupiter, once considered the great inert guardian of the solar system, might not be inert at all. It might be holding on to something ancient, something structured, and now, something warming. As the Jovian probe continued relaying atmospheric telemetry, a consistent anomaly began to appear in its electromagnetic logs. A thin, static layer tightly wrapped around 3I Atlas began showing signatures similar to those seen in deep Earth capacitor arrays, except this was free-floating, symmetrical, and held perfect cohesion even through Jupiter's magnetospheric turbulence. What was it holding back? At first, Mission Control brushed it off as electromagnetic noise, until the probe's outer shielding began reacting, not degrading, but repelling, as if 3I Atlas was wrapped in an invisible membrane that rejected foreign fields. This wasn't a radiation belt, and it wasn't a cometary plasma sheath. It was something else entirely, something architectural. It didn't fluctuate with solar wind speed. It didn't pulse with local magnetic tides. It held. As they looked closer, scientists noticed that this static field didn't just exist, it adapted. When Jupiter's polar auroras intensified, the membrane absorbed the interference and redirected it. Not randomly, but strategically, using Jupiter's own current sheet as a bypass, almost like a natural superconductor. No natural object had ever been seen doing this. The implications were massive. The membrane wasn't just a boundary, it was a filter, a regulator, possibly even a defense mechanism. And if that was true, it meant 3I Atlas was not just surviving the Jovian system, it was calculating its movement within it, based on electric density, not orbital speed. This was no longer motion through space, it was modulation through resistance. From Jupiter's vantage point, this was like watching an organism breathe in silence. The object wasn't pushing forward, it was letting Jupiter do the pushing, absorbing the momentum, and using that stored energy to calibrate its outer shell. Think less comet, more capacitor. And whatever was building inside it wasn't leaking out. Yet. While the static field stunned engineers, a different anomaly was reported from the outer moons. A faint photonic cascade, not in the visible spectrum, but in the near-infrared, was reflecting off Europa, then Ganymede, and finally Callisto in a slow, deliberate rhythm. The timing wasn't random. The sequence was paced, repeated, and oddly, pointed. It took several hours of replay to map the full cascade, but once the pattern was stitched together, the silence in the data room deepened. This wasn't a signal, it was a signature, a rotating spiral pulsed out in light particles, with a core that remained dark, as if whatever emitted the pattern was cloaking its center while exposing its edges. Every loop of the spiral aligned perfectly with Jupiter's orbital velocity, and the duration of each flare matched the rotational period of Europa to the second. Nothing in known physics accounts for this. Comet reflections don't spiral across satellites. They scatter, they burst. But they don't echo on cue, and they certainly don't coordinate with orbital timing. Yet here it was, a 3-point light pattern that moved with precision, as if bouncing from moon to moon not by chance, but by design. Jupiter's ice moons, normally passive reflectors of solar and auroral light, became silent mirrors to this unfolding geometry. Scientists in Italy, Japan, and Chile all independently verified the same signature. Each observatory captured the echoes and each recorded a final pulse that hit just outside Ganymede's shadow. What made this even more unnerving was the alignment. That final pulse didn't trail off, it redirected, and it faced inward. Toward 3I Atlas, as if the moons weren't just reflecting the pattern, they were helping it map something, or someone. The theory forming now was less about 3I Atlas being a visitor, and more about it being a projector, a sender of sequences, a calibrator of gravitational optics, and the Jovian system, with its dynamic magnetosphere and layered satellite chains, might not have been an obstacle. It may have been the perfect amplifier. By this stage, whispers began surfacing in back channels of planetary science circles, not about threat, not about contact, but about mimicry. The idea that this object wasn't revealing its full shape directly, it was letting light, fields, and resistance show us what it couldn't, a kind of cosmic silhouette drawn not in ink but in harmonics, and Jupiter, unknowingly, had become the stage. If you stood above Jupiter's clouds, you wouldn't just see storms, you'd see a living canvas, a slow-turning swirl of colours so vast each storm could fit Earth inside it several times over. But as 3 Atlas passed within visible range, something changed in that canvas. A golden hue began to appear, not from Jupiter's atmosphere, but from above it. It wasn't a glow from within the planet. It wasn't a lightning flash from the deep belts. This golden shimmer reflected off the upper cloud decks like sunlight catching foil, and it was rhythmic. It pulsed. Observatories orbiting near Jupiter's Lagrange points caught the effect with filtered sensors. The colour frequency didn't match any known auroral emissions. It wasn't coming from Jupiter's poles. It was sourced directly from the path of 3I Atlas, and specifically from its tail. Not the long dusty coma trailing behind it like a vapour trail in space, but from a curved structure arching over the object like a halo, glinting and pulsing in repeated intervals. Every time Jupiter rotated 1 degree beneath it, the reflection flickered again. That rhythmic signal resembled something else. Juno, the probe currently in Jovian orbit, had previously detected radio emissions from Jupiter's poles, bursts of radiation aligned with magnetic flux tubes. But this gold shimmer wasn't magnetic, it wasn't radio, and it wasn't just reflection. Spectrographs showed that the shimmer was altering the chemical interaction between sunlight and ammonia ice in the upper clouds. In other words, 3I Atlas wasn't just passing by Jupiter, it was interacting with how Jupiter looked. Now imagine this from the viewpoint of a robotic observer hovering just above the clouds, watching the massive planet slowly rotate. For a few minutes, it would look as though someone had taken a brush dipped in liquid gold and painted soft arcs above the great red spot. Not bright, not artificial, just enough to catch the eye, and then vanish, every few minutes, over and over. Scientists debated whether this interaction was optical, photonic, or something else entirely, an unexplained manipulation of albedo. But for casual observers watching from Jupiter's orbit, it didn't feel like science anymore. It felt like art, or intention. Was this natural? Possibly. Comets do carry fine metallic particles, but why this colour? Why this timing? And why was it only visible when the light bounced at precise angles, almost like a signal meant to be seen only from one planetary alignment? The shimmer was never constant. It never overpowered Jupiter's own brightness. But for those few hours, 3 Atlas didn't just pass by. It painted the planet in a tone it had never worn before. That moment, the gold on storms, would become one of the most discussed anomalies in the planetary sciences community, not because it broke physics, but because it didn't. It used what was already there, and changed what we thought was possible with just light. As 3I Atlas crossed into the region where Jupiter's gravity tugged at its outer tail, something strange began to happen, something involving not the planet itself, but its moons. Io, Europa, Ganymede, Callisto. Each of them has its own story, volcanic worlds, oceans under ice, magnetic fields and tidal friction. But what happened that morning was subtle, barely noticeable, yet unmistakably timed. Juno's instruments began picking up faint electromagnetic pulses, not from Jupiter, not from its radiation belts, but from the direction of each Galilean moon, almost like echoes. Each moon, as it orbited, began producing a faint spike in high-frequency emissions, timed, as it turned out, to the exact moments when 3I Atlas passed perpendicular to their orbital plane. Europa spiked first, then Ganymede, then Io, then Callisto, all within a span of 2 hours, and then nothing. The spikes stopped. No additional bursts. No lingering fields, just a short-lived pattern, repeated across the 4 largest moons of the solar system's most massive planet. Back on Earth, data analysts weren't sure what to make of it. Were these normal plasma wave events, perhaps induced by the way 3I Atlas passed through charged regions of Jupiter's magnetosphere? But there was one detail that didn't fit: the time delay. Each spike followed a precise delay pattern. It wasn't a sequence. It was a staggered mirror of 3I Atlas's position, relative to each moon's centre of mass. In essence, as 3I Atlas passed closest to the moon's orbital path, the moon responded, like a tap on a drum that triggered a perfectly timed echo. What made this even more eerie was the consistency. These weren't strong bursts, they weren't loud enough to interfere with Juno's instruments. But they were detectable, patterned, and most disturbingly, synchronized with the rotational windows of the moon's sub-Jovian hemispheres. That is, the face of each moon that always looks toward Jupiter. It was as if the signal wasn't just bouncing off 3i Atlas, but being reflected through the moons themselves. Now imagine you were watching all this unfold from a satellite near Ganymede. You'd see 3i Atlas gliding silently across the sky, far beyond the orbit of the moon, but your own instruments would suddenly flicker for 2 seconds, then go quiet again. Nothing visibly changed. The comet kept moving. The sky stayed black. But something had pulsed through the space between. Some observers started calling it a tuning fork effect, Jupiter's moons resonating briefly, to the passing frequency of an object that still refused to behave like a comet. Others called it a synchronization anomaly. A few refused to call it anything at all. But one thing became clear. From Jupiter's perspective, 3i Atlas was not a passive traveller. It was a conductor, and the moons, whether by gravity, light, or magnetic interaction, had briefly become part of its score. A symphony that played only once, and only in orbit. As 3i Atlas began to align with the equatorial plane of Jupiter, the massive storm systems of the planet seemed to respond in kind. From the vantage point of a satellite positioned just outside Jupiter's inner magnetosphere, the view was overwhelming, not because of the object itself, but because of what the planet began to reveal. Below the layers of ochre clouds and shifting ammonia bands, a persistent flash began to appear. This wasn't the usual Jovian lightning that erupts within the planet's massive thunderstorms. This was deeper, slower. It pulsed like a rhythm, as if the interior of the planet itself was responding to an approaching beat. It started on January 1st. At first, scientists believed it was an optical echo, a refractive effect caused by high-altitude aerosol reflection. But as the pulses continued, with clockwork regularity and in phase with 3i Atlas's rotational tilt, it became clear this was something else entirely. A feedback loop was forming between the planet's lower magnetic bands and something now present above the clouds, a field so precise it began adjusting the ion ratios within the equatorial zone. The lightning wasn't just illumination, it was pattern. It followed a specific arc, curling around the belts in a motion that mirrored the helix traced by 3i Atlas's tail just 24 hours earlier. The suggestion was profound. Not that the comet had triggered a storm, but that Jupiter had already mapped its behaviour. It had somehow anticipated the field distortion. Atmospheric models fed with this new data began to fail. The giant red spot, long considered a semi-stable cyclone, suddenly displayed a symmetrical spin. Doppler shifts showed a deepening of the vortex in a manner that defied our known equations. But the anomaly wasn't chaotic. It followed a geometry, a fractal convergence that echoed patterns we'd only seen in plasma chambers under extreme magnetic compression. Juno's latest flyby data revealed that the magnetotail of Jupiter, a structure already stretching millions of kilometers into space, began thinning at its edges, not collapsing, not dissipating, but condensing inward, as if the planet was trying to focus, not defensively, not repulsively, but receptively. Down at the Great Cold Spot, an auroral region hidden on the planet's night side, a vertical jet of infrared emission began rising. It wasn't visible in standard optical feeds, but when overlaid against 3i Atlas's inbound light scatter, it formed a cone, a beacon, and at the tip of that cone, the predicted path of Atlas's nucleus. What this meant was still unclear. Was Jupiter reacting to an object that possessed mass and tailing debris? Or was it responding to a field, a form, that we hadn't yet defined? Perhaps the deeper mystery wasn't in the lightning itself, but in the timing. The pulses weren't random. They aligned with timestamps seen previously during 3i Atlas's perihelion spin and Earth-bound magnetic distortions. The same rhythm, the same spacing. The notion that a comet, any comet, could entrain a planetary storm system is absurd by conventional models, but here we were, watching it happen, in silence. With data streams beginning to form a pattern that neither astrophysicists nor plasma physicists had the tools to fully explain. And perhaps that's what made it most unsettling, because the deeper the storm lit up, the more it felt like we weren't watching weather, We were watching dialogue. By midday on January 1st, a strange new distortion had begun to show up in the imaging relays near Jupiter's moons. It was subtle at first, a refraction of background starlight that seemed to ripple, not due to gravitational lensing, but from a localized space density change. And every frame confirmed the same thing. The distortion was not originating from Jupiter, it was coming from 3i Atlas. At first, teams thought it was a flaw, a misalignment of sensor arrays, or a feedback artifact from thermal bloom. But when multiple observatories, including Earth-based infrared telescopes and orbiting Lagrange relays, reported the same interference, the idea of coincidence vanished. What scientists were now seeing was a lensing effect without a lens, not caused by curvature of spacetime in the general relativistic sense. There was no sufficient mass, but instead, a form of dynamic modulation. A cloaked refraction field that seemed to twist background light not by force but by permission. The idea was wild, that perhaps 3i Atlas wasn't just reflecting solar light, but adjusting the field through which that light passed. A form of space frequency alteration, and most alarmingly, it was directional. Only when viewed from certain moon angles, and only when Atlas passed through specific bands of the Jovian magnetosphere, did the effect become visible. The lensing field also affected magnetic readings. Ganymede's onboard magnetometers began to echo with faint pulses, synchronized with the earlier lightning intervals on Jupiter. This created a triangulation opportunity, and what the data revealed was astonishing. The lens was not spherical, it was conical, extending outward in the precise direction opposite the object's tail. And at the cone's apex was a singular point of gravitational silence, not null gravity, but null interference. This suggested that Atlas was not amplifying its environment, it was muting it, creating a zone in which gravitational variance, electromagnetic background, and even neutrino interactions dropped below measurable thresholds. A kind of observation window, one that bent not the light of stars but the fabric between the observer and the observed. Some called it a cloaking veil, others referred to it as a transit sheath. But the name didn't matter. What mattered was what it implied, that 3i Atlas wasn't just passing by Jupiter, it was studying it. And it was doing so through a lens we didn't understand, not built, not launched, but present. The realization sent quiet waves through every monitoring team. Because the implication wasn't just about Atlas, it was about the environment it could create, a field that could alter the way matter and energy were perceived, not by machines, but by the systems themselves. It meant that what we saw was never the full picture, that perhaps all along we were looking at a performance tailored to our line of sight. And now, as the lens focused deeper toward Jupiter's atmosphere, we had to ask, were we ever watching Atlas directly, or had it always been watching us? By the time the second Jupiter sunrise crested across its cloud-split horizon, researchers tracking 3i Atlas from the Jovian shadow had already begun to notice something unexpected. The object's silhouette, seen from Jupiter's vantage point, didn't align with the standard expectations of a nucleus-bound comet. It wasn't spherical. It wasn't chaotic. It wasn't even fragmenting like most comets under solar strain. Instead, the shadow it cast appeared angular, geometric, and that changed everything. At first, many assumed the discrepancy was an artifact, a quirk of angle, or maybe a miscalibration in the synthetic aperture imaging arrays orbiting the gas giant. But once those early impressions were corrected, the geometry remained. Crisp edges where there should have been none, symmetry where entropy should have prevailed. The object's penumbra, when traced across Jupiter's upper atmosphere, created shadow intervals that didn't match its observed rotation. This meant something subtle yet profound. Its visual body and its gravitational core might not be the same thing. It was as if 3i Atlas was hiding an interior mass not visually accessible through conventional spectrum bands, but one still dense enough to cast influence. That influence was felt most clearly in the patterns of trailing particulate it left behind. You could see them better from Jupiter, thanks to the contrast provided by the planet's swirling ammonia bands and deep red hues. From that position, 3i Atlas dragged what looked like a soft ring of dust, not behind it, as typical tail mechanics would suggest, but around it, orbiting, not trailing, as if it weren't shedding debris, but holding it in place. The ring itself, though faint, moved in such a calculated rhythm that it gave the appearance of stabilization fields. Nothing known in cometary science accounts for this. Objects that fragment or disperse due to heat or velocity don't maintain coherence. They fall apart, they decay, they spiral chaotically into entropy. But 3i Atlas didn't spiral, it orchestrated. From a shadow analysis perspective, the anomaly deepened when researchers began overlaying that geometric silhouette with historical images taken from Earth-based instruments. Shockingly, the same angular signature was visible months earlier, but hidden within the object's brightened coma, made invisible until the light contrast of Jupiter allowed the shadow to isolate it. And the shape wasn't random. It was a hexagon, not perfect, not machine-made, but undeniably consistent. Each return of the object's rotation period brought with it that same 6-point geometry, shimmering like a whisper behind the plasma arcs. It matched no natural outgassing pattern ever recorded. It followed no known ice-fracturing geometry. It wasn't chaotic enough to be dismissed as coincidence, and that led to the deeper implication that maybe the geometry wasn't accidental, maybe it was structural. That single possibility lit a fire across scientific forums the world over, especially within deep structure simulation teams and planetary engineers. Could a naturally occurring object evolve into geometric self-stabilization? Could gravity itself etch stability into a mass so volatile? No one could say for certain, but from Jupiter, the view was clearer than it had ever been. Not just visually, but contextually. Here, away from Earth's magnetic field, away from solar noise, the lens of perspective shifted, and what Jupiter revealed was more than a shape. It was an intention. As the observational teams began collating multispectrum data from the Jovian moons, a separate thread of discovery began to unfold, not in the visual realm, but in magnetometry. Deep inside the dense magnetic field of Jupiter, there echoed a signal. Faint, periodic, and unlike any auroral resonance previously mapped in the gas giant's history. It started as a whisper, a low-frequency harmonic that emerged near the northern polar cusp of Ganymede. At first, it was dismissed as background noise, likely originating from the turbulent interactions between Jupiter's field and solar wind. But then it repeated, then it amplified. The signal wasn't random. It occurred at intervals that matched the rotational rhythm of 3i Atlas, not its rotation around the Sun, but a sub-frequency pattern embedded in its physical spin rate. Every 23 minutes the signal returned. A low, subaudible hum recorded not just on Ganymede, but, soon after, on Callisto, Europa, and Io. Its directionality was impossible to ignore. It wasn't broadcast like a flare or dispersed like radio emissions from Jupiter's own flux tube arcs. This signal was tight, focused. It behaved less like a noise and more like a radar ping, emitted, refracted, and returned. But here was the twist that no one anticipated. The signal didn't originate from 3i Atlas directly. It came from its tail. The magnetic emissions were traced to a curvature point in the object's reverse plasma arc, a tail that no longer flowed away from the Sun, but bent inward toward Jupiter. The tail had never behaved like other cometary discharges, but now it had become more than a trail. It was a transmitter. Researchers proposed a range of speculative mechanisms, plasma sheath oscillations, localized flux compression, tail electron harmonics, but nothing explained the precision. The tail's magnetic pulses echoed not in broadband spread, but in intervals that matched the rotation of Ganymede's magnetosphere. That's a level of synchronization that goes far beyond what any natural process has ever displayed in a transient object. Some argued it was resonance coincidence, others whispered it was modulation, an attempt at some kind of energy calibration. But no theory accounted for the directional flow of the pulses. From Jupiter's side, the tail emitted toward the planet, then bounced the residual echo toward the moons. That kind of tracking, magnetic, coordinated, and adaptive, requires awareness, or something akin to it. When observatories stitched the signal maps across several Jupiter days, a clear triangulation emerged. Each echo passed through an optimal magnetic path. First Europa, then Ganymede, then Io. It skipped Callisto entirely. Why? No one knew. The best guess? The field strength there was too low, which meant, if that were true, 3i Atlas wasn't just emitting a magnetic pulse, it was targeting strong field regions to bounce the signal forward, like sonar, like a network ping searching for a response. That alone would be enough to destabilize every comet model known to science. But it did something else too. After each echo, the object realigned its outer shell, barely noticeable at first, just a shimmer, a reorientation of plasma distribution, but consistent, predictable, responsive. The tail emitted, the signal bounced, and the object adjusted. That wasn't passive behavior, that was interactive calibration. And as the magnetic echo settled across the field sensors, the final realization hit home. 3i Atlas wasn't reacting to Jupiter, it was using it, and whatever it was tuning toward still hadn't arrived. And so, as we drift back from the clouded limbs of Jupiter's stratosphere, where pressure becomes colour and the sky folds into motion, we're left with a final image, a theatre silent in its performance, where 3i Atlas played not to applause, but to gravity. It had not come to Jupiter seeking collision. It had not come for heat, or mass, or even magnetism. It had come for scale. Because Jupiter, more than any other planet in our system, represents the boundary between what's terrestrial and what's interstellar. It is the solar system's amplifier, its bouncer, its archivist. And anything that passes near its domain either gets swallowed or seen. From here, 3i Atlas was seen. We watched the way it lit up the upper bands of Jupiter's auroras, not in the usual ultraviolet spectrum, but in something more layered. A deep field glow that moved across latitudes like a scan line, shimmering in reds, then blinking in green. It wasn't a beam, it wasn't even a broadcast. It was the visual residue of interaction, a signature of proximity, not purpose. And in that moment, what became clear was not the threat, not the trajectory, not even the science. It was the scale. Because from Jupiter, 3i Atlas was not large. It was not powerful. It was not terrifying. It was precise. It aligned with magnetic ridges it shouldn't have known. It mirrored the ion cyclotron resonance between Callisto and Europa. It veiled itself in harmonics that wrapped around the great red spot without dispersing. It wasn't dominating the Jovian system. It was adapting to it. And then came the silence. For 15 hours straight, longer than any of its previous tail inversions, jet pulses, or alignment shifts, 3i Atlas held position. No spin, no expansion, no decay. It was as if it had entered a holding pattern, waiting for something, or watching. From Earth, that stillness looked like a lull. From the Moon, it looked like a freeze. But from Jupiter, from the orbit of Ganymede and the magnetic flex of Io, it looked like rehearsal. Like 3i Atlas had paused its movements not out of exhaustion, but calibration. By the end of the first day of the new year, Earth-based observatories began picking up faint distortions again. Not light, not heat, not jets, but shape. The tail had bent again, only this time not from solar wind. It had curved into a toroidal loop, circling its own head like a serpent swallowing intent. And from Jupiter's vantage point, the loop looked like a lens, not metaphorically, literally, a curvature of gas and ionization that magnified the starlight behind it, refracted, bent, directed. That lens never faced the sun. It didn't sweep the asteroid belt. It didn't point towards Saturn. It pointed directly toward Earth. But from Jupiter, that didn't look aggressive. It looked ritualistic, like something finishing a sequence, not declaring war, but declaring function. As if to say, this is what I was made to do. And maybe that's the part that still rattles the edge of astrophysics. Because every simulation we've run, every paper peer-reviewed, every whisper between heliophysicists across midnight screens, none of it predicted this. We expected decay. We expected ice scatter. We expected fragmentation. But we didn't expect choreography. And certainly not from something that shouldn't have lasted this long. So what do we do with that? What do we do with the idea that 3i Atlas wasn't simply a visitor but a participant? That its passage through Jupiter's domain was less about trajectory and more about timing? We can measure it, we can model it, but we can't answer it. Because to answer that would be to claim we understand intent, and we're not there yet. Not from the shadow of Jupiter, not from the echo of its moons, not from Earth, and certainly not from the digital frame of this video. But here's what we can hold on to. We were witnesses. For a brief window of time, we saw something that reframed not just how a comet moves, but how a structure interacts. We saw a tail bend in alignment with a planetary ring current. We saw auroras echo signals that didn't come from the solar wind. We saw timing that mirrored lunar orbits, not solar ones. And we saw a stillness that wasn't inert, but deliberate. Whether 3i Atlas is natural, artificial, or something in between, it is now part of the story of Jupiter, and Jupiter in turn has become part of the story of us. Because whatever comes next, whatever Atlas does in the days ahead, whether it turns again, burns off mass, or vanishes into the vacuum, it's already changed the way we look outward, not just in direction, in expectation. This has been another deep space moment from the voice of this channel. If you're still listening, thank you. Let me know in the comments where on Earth or off Earth you're watching from, and tell me, if you were on Jupiter, what would you want 3i Atlas to see in you? Until the next anomaly, stay curious, stay human, and stay watching.